Okay, so we will have our last topic this morning, which is the AFM based dynamic mechanical analysis, the so-called AFM DMA. And the DMA is used to measure the viscoelasticities, but in the frequency domain. So this morning, I think we just need about 2 hours or 1.5 to finish the principal part, and then we can go directly to the hands-on session and on this techniques. So as we said yesterday, we can use we have some materials. Its modulus or stiffness is a function of time. Modulus or stiffness is a function of time. As such, we can describe how it changes against the time. So we have a time domain technique, and this time domain technique is used to describe the two phenomena people observed in the experiment, which is creep and relaxation. And the creep and the relaxation is if we fix a stress, we say how the strain change, or we fix this, I give it a strain. If we fix the strain, we say how the stress is changing. And from this we can detect how the modulus is changed against the time. And the people widely use the Maxwell's model to fit this modulus change against time to deduct the so-called Maxwell model. Usually they write it down in such exponential function. And their key idea is to figure out this modulus and the viscosity. Usually they represent this in a way of lifetime, but it's the same thing. So from the Maxwell model, people can tell, okay, what's the viscous part and the elastic part distributed inside this material. But usually this kind of explanation or description seems so mechanical, so theoretical. Inside our materials, for example, we have the example yesterday, we're using the PDMS. Inside the PDMS, it's hardly for us to detect this part is a damper, this part is a spring. It's hard to figure out which part is damper, which part is viscous, which part is like a spring, just based on the chemistry structures. So this kind of time domain description is seems like too mechanical. And on the another side, this time domain, if we do it experimentally, we found usually we need to take a long time to finish this experiment because you observe it against time, so you need to wait. And if we are doing something like cells, gels, like those soft polymers, it's okay. But if we are doing something for really kind of hard materials, like the bones, like the cartridge, that's a different story. It will wait for a long time. So people develop a so-called a frequency domain. And the frequency domain, they need to introduce they need to introduce the time in another way, which is frequency. Or when we do it in the experiment, we introduce speed. So if we just consider at different speed, how this materials responds to my force, and that's the way we can also measure the physical elasticity. And this way we call it a dynamic way. And as such, they define their name as dynamical mechanical analysis. That's the DMA. So for DMA, usually when you watch out that marker scale DMA in our facility, you can see it will also have a stylus, and you put your samples on the sample plate, and this stylus can apply force on your materials, but now time, but this time it's not a constant force, but as a dynamic force or a periodic force, something like this. And then we do the same thing. We observe the deformation change, and the deformation change should also be infrequent, or in this kind of oscillation. And from the stress and the strain we have, we also give out the modulus. But since we do it in this kind of dynamic way, or we do it in this periodical way, the mathematical process will be a little bit different. So the first, we need to introduce the mathematical way to describe this kind of dynamic analysis. So usually people starting from this. Nowadays, we are not apply a constant stress or a constant strain. We just give it a periodical way. And since the simplest periodical way is we can define it as a sine wave. So we just give our stress, give our force in a sine wave way. So for example, like this left side, we apply our force, will stress in a sine wave way. And the omega t is defined by ourselves. We define such frequency. And then we measure the deformation. And from the deformation, we get the strain. And the strain should also be a certain wave. But the problem now is we do not know if the sigma and the epsilon, it is the same phase or not. So we just assume there is a phase different. And the idea is we need to figure out what the delta looks like. So we can define the Young's modulus easily. So our Young's modulus should be the sigma 0 divided by epsilon. And then we have a sine omega t minus sine omega t plus delta. Okay, that's our ideas. So that's the way we can get the modulus out. And then we're starting from something we know very well. So we're starting with the pure elastic. For the pure elastic, we know we have Hooke's law. The sigma equals to the modulus times the epsilon. And the modulus is not a function of time. So I can easily write down once the epsilon is a function of time, it should be directly write down. And the sigma, it is sigma 0 sine omega t. So as such, we can easily detect the delta is 0. And so for the pure elastic, the sigma and the epsilon, it is in phase. When I apply larger force, my stress will be, my deformation will be larger. When I apply small force, the deformation should be small. So it is completely in phase. And then we take a look at the fluid. So if we study the pure viscous, so if we're studying the pure viscous, the force and the deformation, they should follow the Newton's law, the Newton's fluid law, which is the force is proportional to viscosity times the speed. So in our case, we write down as the sigma equals to eta s d epsilon over dt. So for this one, we need to take a derivative of epsilon. So the sign should be changed to the cosine. And as such, we know the delta is half pi or 90 degrees. So with the pure elastic and the pure visco for the pure fluid, and the people detect the phase should be a good signature for the properties. So if we can measure the delta, we may be able to describe how the viscous this material is. If the delta is close to 0, means we are measuring something like a pure elastic. If we get the delta is close to 90 degrees, we say the material is like a fluid. It's quite, it shows viscosity as a main component. So for this kind of modulus together, so nowadays for the modulus measured in the dynamic, they call this complex modulus. The idea they introduced the complex number here is just due to a difficult way to solve this out, to solve this equation out. Because inside this, from our experiment, we get our effective modulus is something like this. We cannot get rid of the time easily. So we decided to change the sine wave back to the exponential using Euler formation. So we can just use we can just use Euler equation to easily replace this signs, go to the exponential, and then we can easily get rid of time. So for example, for this one, if we write it down in the exponential way, so our sigma, we can write it down as the sigma 0 ei omega t. Yes, we are write it down in a complex way, and in the experimental, we only observe the real part. The imaginary part will not be observed in our experiment. But in mathematics, it does not harm. We write down this kind of the phase relationships. So for this one, we can also write it as the epsilon 0 ei omega t plus delta. And then the modulus can be written down in a complex way. It's sigma 0 divided by epsilon 0 and times ei delta. And this will be our final way to express our modulus. And we call this modulus a complex modulus. And of course, it has the real part. The real part goes to the cosine delta. And the imaginary part is the I sigma 0, epsilon 0 sine delta. So as the people introduce the complex or the imaginary, they want to represent those kind of time difference. So in the in the mechanical, they call the real part storage, and they call the imaginary part noise. And the storage in the mathematical, they want to represent, they want to say this is mainly due to the elastic. Because if we look it back, if the delta is 0, the modulus should be pure elastic. So once the delta is 0, we only get the real part. So the real part represents the elastic. They call it storage. And for the imaginary part, they call it noise because it shows viscosity. And the viscosity is hydrodynamic force, is friction, it's wasting your energy. So they call it the noise. And the loss is the same. If our delta is half pi, it's 90 degrees, the real part should be 0. And we only have the imaginary part left. And so the imaginary part represents the viscosity part. So we have the storage and the noise. And as such, this delta, we gave it a name, the noise tangent. It's just the imaginary part divided by the real part. And we call it noise tangent. And the noise tangent, just the same as the delta, is used to describe how viscous our material is. The larger this value means the more viscous our material is. So that's the classic DMA done. So for the DMA, the experimental is something like this. Quite easy, quite easy. Of course, nowadays we do not use a camera to watch the deformation. They will place a position sensor here. They will place a position sensor here, so it knows the stylus is moving up and down, up and down, up and down. As such, it records the deformation. So our stylus measure the force, the position sensor measure the deformation, and we define the section area, we define the height. We can transfer it to the stress and the strain, and then easily get this part out. And then for this part, we change it to the exponential game, and then we get the storage and the loss and the loss tangent. That's how the DMA is done. And if you go to that machine, I think in the second floor, and we have the DMA in the facility, you just we will see something like this, and you just put your sample there, and click it, it will start to do the measurement. And since it's starting from a frequency domain, so the total idea is they may want to so we have a time domain stuff. And our idea is we may want to change the time domain stuff to a frequency domain. And the easiest way or the most widely used way to do this is we do the Fourier transformation. And for the Fourier transformation, we change the time domain stuff how we do that in the mathematics. For function, we change it to for a series of different frequency summation, right? So for time, we need to change to a continuous to a continuous for a spectral on the frequency domain. So actually, a time stuff, we also need to show it in a lot of frequency in the frequency domain. So basically, we should not just do one frequent, but we need to do a serial numbers of frequent. And the highest frequency, can be done is decided by our machine. So usually the macro scale DMA is down to, I think it's 100 Hertz. And if you want to do it more locally, you can choose the larger indenter. The larger indenter goes up to 300 Hertz, but that's about it. And the AFMs, the facilities icon, they can provide you two options. The first is also from 0 to about 100 Hertz, and we have a high frequency option, right? And the tiny one be behind the stage. Yeah, we have that. Yes, the tiny one goes up to 20 kilohertz. So yeah, so the AFM's large DMA significantly expand the frequencies domains of it. Yeah. So that's about the basic idea of how we done in the macro scales, and for the AFM, the story is a little bit different. Is as Dr. Ma yesterday said, we cannot measure deformation directly. We are measuring the scanner movement Z. We need to measure scanner movement Z, and we need to measure the deflection. And from the difference of them, we get the deformation or indentation is the same. So for the macro scales, they can directly measure the deformation. They can directly measure the force. We can measure the force from the deflection and the vertical. But for the deformation, we have to measure the Z and the deflection together. And then we minus them, we get the deformation. So the mathematic process is, if you take a look at the AFM manual, it is relatively long. So we write down in such way. We play the same game as the DMA did, but nowadays we cannot make our sample to a fixed shape, so it's randomly. So since it's randomly, so we don't have a fixed section, we don't have a fixed height, we cannot get stress and strain. So we will play the same game as the force curves. We get the stiffness out and use contact model to calculate modulus. So we get stiffness and then Hertz model. So we leave the Hertz model to the next step, and we get the stiffness out first. And for stiffness, it is force and deformation. So we have our stylus, which is AFM probe, and we can apply a theoretical force on the samples. But again, we cannot directly control the force. We can directly control its scanner. So we make our Z movement now is periodical. And as such, we observe the vertical change. The vertical change now is V0 sine omega t plus delta. It should be a frequency. And this frequency may not be the final frequency because we need to minus them to get the deformation. So this delta may not be our final north tangent delta. So I use this one to represent the phase change. Okay, so then what we have to do is we need to first get the deformation. And the deformation is Z0 sine omega t minus V0 sine omega t plus phase. And this is just vertical, so we need deflection sensitivity to change it to deflection. Okay, now we are playing a mathematical game. We have sine omega t, we have sine omega t plus theta. You need to minus them. You still remember the mathematical games about sine A plus sine B equals to sine A cosine B plus cosine A sine B, right? We can play the game, and I hate it. We don't want to do the games. So Brooke did the game for you. Brooke did the game for you, and it makes a quite long equation. Don't need to remember them. We can do it in a different way. Is we just do we can just do the exponential way at the beginning. So we write it down not in this form, but in exponential z0 I omega t. And this one is V0 ei omega t plus theta. So our deformation is just Z0 ei omega t plus minus deflection sensitivity times V0 ei omega t plus theta. And the force will be equals to the vertical times deflection sensitivity times spring constant. So will be the spring constant times deflection sensitivity times V0 ei omega t plus theta. And then we have force, we have deformation, so our stiffness is out. So it's just Kc deflection sensitivity times V0 ei omega t plus theta divided by Z0 ei omega t minus deflection sensitivity times V0 times ei omega t plus theta. And the ei omega t can be reduced. So we finally get, it's just relatively easy. It's still not that easy, but it's much easier than that one. V0 ei theta and the Z0 minus deflection sensitivity times V0 ei theta. That will be our final stiffness. And the stiffness, you can use the similar concept. We call it a complex We call it a complex stiffness. And as such, you can, from this, you get the storage part, the real part, and the imaginary part. And the final one is read out like this. That's our final results. That's our final results. So we have the real stiffness and the the real stiffness and the imaginary stiffness, and Brooker calls the same name, they call it the so-called storage stiffness and the North stiffness, but nobody called that. It's just a Brooker, because Brooker used the way to get the stiffness out and then Hertz model. So they have the real, so they have the stiffness out, and then we can have our the modulus later. So that's how Brooker process this number. So you may need it when you publish the paper, and you can just use this in your method part about how Brooker process the number. And of course, you don't need to really remember those kind of equations because it's done by softwares. And you can just easily, what you have to do is just you set up the Z movement, and the AFM will measure the vertical part, and the software will give you your results. And of course, we need to do the calibration of KC. We need to do the calibration of the deflection sensitivity, absolutely. Yeah. And then the next step is relatively easy. We need to get the modulus out. So we still take Hertz model. The modulus is equals to the stiffness minus 2AC. So for the AC, the gain back is again, we need to know the shape of our probes. So if we are using cone, we use slider model. If we are using a column, we use the radius of the column. If we are using sphere, we use the radius of the sphere. That's the same game. Yeah. So that's why mostly in the nanoDMA, we need to use a defined shape. We need to use a defined shape, because not like the QM or Fosco, we can use random shape is okay. We can use the relative method, but for this one, we prefer to use a fixed shape. We use a fixed shape. As such, the AC will be fixed. So that's just the end of the story about the theoretical part. So we need to do calculation first. We need to do calibration first, and then leave it to the software. Okay, so that's about the part, and then how we do it. How we do it. We do it in similarly as we explained yesterday. We still need to hold our probe on the surface, and we need to stay for a while. So we need to hold it for a while. And during the hold, we need to apply this kind of modulation or the periodical force. And after that, we can retract and get the force down. So the nanoDMA is based on ramp and hold. So it's based on ramp and hold. But usually, when people did DMA, they will do a series of frequencies. So this one, they will also play the same games. So they will measure the series of frequency. And as such, we need to make a script of which frequency we want. So it's ramp scripting. So finally, we will face, sorry, I will jump to the software first. We will do the ramp scripting game. And in the ramp scripting, we need to define how the probe touch the surface, and then we will do a serial frequencies, not just one, but do 10, or 20, or 100, as much as you want, and you type the frequency here, and we can generate a script. And when we do the script, when we during the hold, the probe will do the modulation at different frequencies. And that's how we play the nanoDMA games. Okay, so let's go back to say the hardwares. And the hardware is something like this. We have the blue one. The blue one is marked as a heater. It's used to change the temperatures, like the macro scales DMA do. They can change temperatures and to do it. And then we have a high frequencies actuator, a tiny one be next to the heater. It can change the frequency up to 20 kilohertz. So if we're not using this one, we can only go to about 300 hertz. And with this one, we can go to 20 kilohertz. Okay, so for DMA, so usually for DMA, it always include a heater. So why the heater is widely used in the DMA is due to a principle, and this principle is called temperature time superpositioning. And if you read the reference, it's just called TTS. It's just called TTS. And the TTS is a kind of principle used in the viscoelasticity materials. And it tells me, it gives a brief idea that the temperature and the time, they can be the same thing. My colleague, there's once used to work with us in Broker named Peng Fei. He gave an idea about how we explain the TTS. I'm not sure if I translated it correctly. How to translate the 公仔面 in English? Yeah, instant noodle. Yes, instant noodles. Yeah, you know the instant noodle is after fried. It's kind of it's hard, it's solid, it's compressed together. And for the instant noodles, we need to make it soft, make it edible, right? So for those kind of for to prepare the instant noodles, usually the manual told us you can add boiled water, 100 degrees C, and maybe 2 or 3 minutes. It's done. But you know, when you when I studied in my undergraduate students, and every night people will go to the shop to buy those instant noodles, and then we need to wait for the boiled waters one by one, and nobody wants to wait for there. So sometimes the water is not boiled, it's maybe 80 degrees. We'll stop and take the water out, so the water will never be boiled. But if we use the 80 degrees C water to prepare the instant noodles, we need to wait maybe longer times. And finally, we get the noodle prepared. It's soft, it's eatable. So the final results is about the same. So if you have the high temperature, you can just wait for short time. If you have the low temperature, you can wait for long time to get this kind of instant noodle out. The instant noodle is those kind of soft chains that tangled together. It's the similar as our polymer. So the polymer inside this kind of quite plastic, quite hard materials is just those polymer chains that tangle together quite tightly. If you heat it, it will melt down the molecules chains, it will loose and release just like our instant noodles. So the game is the same about the TTS. So high temperature means short time waiting, and the low temperature means long time waiting. It's the same. It's the same principle. So high temperature can did the low speed stuff. It can take the effect as the low speed. If you are doing it slow, but if you give it high temperature, it can reach the same effect. If it's low temperature, if you give it high speed, it can reach the same effect. So that's how we said about the TTS is the high T is similar to the low frequency. And the low T means high frequency. That's why in the traditional DMA, they don't need to use the high frequency stuff because they can reduce their temperature. If they reduce their temperature, they can think, I obtained the data at high frequency. And the Brooker did the opposite way. I do not introduce a chiller, but I introduce a high frequency stuff. And then from the high frequency stuff, I can get the property at a low T. But to be honest, the high frequency actuator is not that popular in the community. Maybe our facility is just one or two purchased the high frequency actuator in Hong Kong because the community, they do not need such high frequencies. Such high frequencies is almost near the temperatures, maybe in Marshall or something. It's really low, maybe negative 200 degrees C. So it's really low temperatures. So it's really low temperatures. Such low temperatures, we don't have much engineer applications because people use it to study the DMA for tiles. And the tiles, the daily temperatures, if you drive it, even you drive in Canada, it's maybe just negative 20 or 30 degrees C. That's about it. And if you drive it in Africa, maybe you can reach 40 or 50 degrees C. That's it. That's the daily temperature they need to use for tiles. And the tiles is the mainly polymer consumers. So the scientists and the engineers, they use DMA for tiles. They just need that short time windows. But nowadays, for scientists, you can do anything you want. You can study the tiles property in Mars. So Brooker introduced the 20K hertz, some due to the financial to make it different, and some maybe due to the scientists, they want to do something differently. So we have the 20 kilohertz. Yeah, we have the 20 kilohertz. So ideally, people use the temperature time superpositioning, the TTS, to make this the frequency spectroscopy to be complete, because they can only measure from 0 to 100 hertz, you have a long frequency, you need to change temperature. So people use TDS to make a full spectroscopy. So that's about our hardwares. So the hardwares is so in the afternoon we can do the experiment, and we can try the heaters, we can try the actuators. Okay, so the software is very easy. We can adjust the temperatures just using the heater. And the book described they have several types of modulation, but it's the principle is about similar. And the thing we need to discuss here is we highly recommend you to use the spherical probes as the radius will be fixed. Why we insist on that? So the total idea is we get the stiffness out. And once we want the modulus to be stiffness divided by 2AC. And AC is not a constant. And if we are using the say Hertz model, it's a sphere. The AC equals to radius times the deformation. The deformation is larger, the contact area will be larger. So AC is not constant, it's a function of the deformation. I'm sorry, I changed delta, but gave it to deformation, okay? And even we are using the slider model, we think it's a cone. It's also equals to the deformation times tangent alpha. So the point is the AC is a lot constant. It's a change of time. But we know our stuff. We know we are facing polymer material. We are facing the viscosity, viscoelastic materials. So its modulus will change. And in other words, the sample itself has creep. Once we hold the probe on the surface, the sample will start to creep. If the sample is creeping, we will say the deformation is changing against the time. So the probe will penetrate deeper, deeper, and deeper. As such, the contact radius cannot be a constant value. It will also change against the time. So once we change the contact radius, we are actually measuring the stiffness. So we need to figure out the contact radius, how it changes against the time. So ideally, we want to get the AC change against the time curve. And then we can get the modulus correctly. If we stay at the stiffness, it's okay. But we want modulus. We need to get the contact radius out. And of course, you can use the column probes. If you use column probes, the contact radius is always constant, right? If you use a column shaped, the contact radius is just the radius of the column. Yeah, but no, we don't use that probe because that will sacrifice the resolution too much. So we use cone or sphere. We were facing the situation. So how Brooke did it? So the Brooke did it in this way. Sorry, let me see the slide. So Brooker made the recommendations in this way. So when we do a force curve, we let the probe to hold on the surface and then hold for a while. And at the beginning of this hold segment, usually we would let the probe to hold for a while. So let it creep for several seconds. I'm sorry, wait, I should not use this one is the force. This one is Z, and the Z write it down, okay? So I'm starting the hold. And in principle, we need to do the modulation. So we're supposed to do modulation at this time. And then we observe the modulation of the force, but not suggested by Brooker. Brooker would suggest you to wait for a while. Hold the force, wait for a while. And once we hold the force, the sample will definitely creep. And during the creep, because for the creep, it decayed fast at the beginning, and later it will slow down to be relatively stable. So we will just stay maybe 30 or 50 seconds. And then we start to do the creep. To do the modulation. And for that, we can reduce the effect of the creep, but it's not eliminate. So the Brooker introduced a way called reference frequency. I call it FR. So this reference frequencies, you can say in my hands-on session later, we type in here the reference frequency. This reference frequency is used to get out the contact radius. So the idea is, for example, this is time. This is our time. So we did some frequencies, and we gave it a reference frequencies at the beginning, and we make it in the end of the force curve. Okay. And then we starting with the reference frequency, we ended with the reference frequency. And inside this this scripting, we can do our designed frequency we designed. For example, we want to do 1 Hertz, 10 Hertz, and 90 Hertz. We can do 1 Hertz and then 10 Hertz and 90 Hertz. And we get 3 Hertz down. And then we reach our FR again. And from this force curve, we can get the contact radius at the end of the force curve using a polymer model called JKR. And that model is we can calculate the contact radius from the adhesion force. And so from this model, we can get the contact radius at the last segment which is FR. And so we can get this is FR at the beginning and FR at the last. And so from this FR, we will followed by a retract. Sorry, retract is red. And so at this time, I can get the contact radius out from adhesion force. And at this AC, I have the stiffness, so I can get the modulus out on the reference frequencies. And this reference, the modulus at this reference frequency should be equals to the frequency, reference frequency at the beginning. So at the beginning, I can also get stiffness. And the stiffness at the beginning, at the end, they may not be the same because the radius is not the same. So from this, I can get the AC at the beginning. So as such, I have the AC on the beginning. I have the AC in the end. I have the AC against the time curve. And then I can tell the AC on 1 Hertz, AC on 90 Hertz, 10 Hertz, and AC on 90 Hertz from this curve. That's our idea, is using the reference frequency to define the AC change against time. And then every time you have an AC, every time you have a stiffness done by AFM, you can get the modulus correctly. That's our idea of setting the reference frequencies. So ideally, to set up this the reference frequencies, the concept we need to avoid our AC frequency. What's the AC frequency in Hong Kong? Is 50 or 60? 50. Okay. So 50. We should to avoid 50. So the reference frequency, we would avoid 50 or 100 or 150 or 200 stuffs. So usually we will set up this reference frequency as 90 or 110 to avoid the AC. And this manual is read down by US guys. The US guys, they use 60. So they recommend 100. But if you're doing in Hong Kong, I would recommend 90 or 110. And then that's the other stuff is relatively easy. So we need to set up the frequency range, set up the reference frequency, and for here, we need to set up how we want to modulate our samples. We need to apply a force first, and then the force will cause a deformation of the sample, and then we need to modulate our materials. So we would apply a force at the beginning, and then we will hold the force. And during the hold, we will do the modulation. And the idea here is we don't want to introduce a large modulation. As such, we would change the deformation too much. So we want some tiny modulation. We don't want the huge modulation. So usually the modulation force should be about 1/5 of the force we applied, and the software will automatically adjust the force for you. For example, if you want the maximum force to be like this nice, give it a 30 nanonewton. The software automatically change the modulation force to be 6 nanonewton. So you can apply a large force, cause large deformation, and a tiny modulation force to change the deformation quite tiny. As such, you can measure the DMA correctly. Yeah, it's the same as the macro scale DMA. You don't want the modulation to damage your sample dramatically. Okay, and for here, we need to define the ramp size is the same as the force curve and the velocity, and we need to define the relaxation segment time. Let's let it to creep, and the other stuff we can explain in our hands-on sessions. That's about the nanoDMA spectroscopy. And this is done using the ramp scripting. And after that, we can get out this kind of spectroscopy of vertical and the Z. It changes. It shows different segments. This is low frequency segments. This is high frequency, higher, super high, and then from each segment we can capture we can get a modulus out. We can get the storage modulus and the loss modulus and the tangent delta. Yes, and the tangent delta. And finally, it will generate this kind of spectroscopy. The modulus against the frequencies changing from low to high. Yeah, usually it's something like this. The viscoelasticity we observed yesterday in most examples, due to the as showed by the Maxwell model, is the modulus will decay against the time. Once it's stay longer, it will be softer. And so now today we are doing the frequency domain. So as the frequency increase, the modulus will increase. That's your life feeling. If you punch something quite fast, you can sense it's hard. If you touch it gently or slowly, you sense it's soft. Yeah, that's our daily experience. So usually we should be able to observe something like this. The modulus will increasing against the frequencies. But if you find it different, if you find it decreasing, maybe you did it wrong, maybe you did some weird things. So yeah, that's the idea. And we can also use the nanoDMA stuff to do the mapping rather than just to generate a script. And we can do mapping. And to mapping, we are using the force volume stuff. And on each force curve, we will add a ramp and hold. And inside this hold, we will introduce this kind of modulation. And inside the modulation, of course, you need to define the modulation force and the modulation frequencies. And then we can generate a mapping of storage modulus, loss modulus, and the loss tangent on your defined frequencies. So sorry, so if we're doing the spectroscopy, is we done in one point, generate property at different frequencies, or we can do a fixed frequencies, but on different area, different point to get a mapping. So that's the idea. So this nanoDMA has to be done on a so-called Brooker's mirror view platform. I'm sorry, I have to say that platform is relatively quite slow. So it's not as fast as the other workspace. So this afternoon you need to be some kind of patient when you're facing the mirror view. Okay, but the mirror view has its advantage. You can usually in the AFM we are just looking at a certain area, and we don't know what's the other area. We cannot change area easily, but with the mirror view we can see the relative positions of different scans. So it has its advantages. Okay, that's about the nanoDMA. So the key idea is we use dynamic ways to do the force curve, and we introduce a modulation, and with the ramp and hold mode, and we introduce the ramp scripting to generate the spectroscopy. We use the force volume to generate the viscoelasticity mapping. And finally, we can get the viscoelasticity properties. And I would say it is widely used for polymers. And we can do it for cells, it's okay. But mainly the main topic is about the polymers. And if our researchers they want to study the materials combined with several polymers or polymers with other materials, they may be interested to see how the boundaries looks like, how they linked together. Yeah, that's about these techniques. So I think I'm done with all the theoretical part, and we will continue the hands-on session in the facilities icon. And so I just leave all the slides on the PCs, okay? Yeah. So if you need, you can just use these slides for the reference, okay? So I think that's all the theoretical part. Thank you for your listening. Thank you.